I don't know if you were at the first talk. You probably noticed I didn't quite get to where I wanted to be at the end of that first talk. I think I alleged that I would sort of start this talk with the punchline that I didn't really deliver in the last talk, but I think I won't do that. Maybe it will come later. What I wanted to, so the last time I talked about general features of elliptic cohomology, and then towards the end, and I tried to emphasize the idea that there's this interesting question about what power operations look like for that theory. So there are a number of cases where we sort of know how power operations work, special cases. One of them is elliptic cohomology associated to deformations of supersingular curves. And that even extends to equivariant elliptic cohomology for that curve, as long as you just look at finite p groups. And the reason for that is that that equivariant cohomology theory is really just a Borel cohomology theory for something called Ravi E theory. So what I want to describe today is the theory of power operations from Ravi E theory, which was set up in work of Ando, Hopkins, and Strickland. So that's the plan for today, at least the first part of today. So I'm going to talk about formal groups, as I've been doing. So I'll talk about formal groups over a ring. Maybe G over R is going to be a one-dimensional commutative formal group. We can talk about homomorphisms between two different formal groups. There's one particular kind of homomorphism which is very important if you're looking in finite characteristic. So let's suppose that R is of characteristic P. Then we have a homomorphism called the Frobenius homomorphism, which works like this. So I have an absolute Frobenius map. This is the absolute Frobenius map on the ring R. And now if I start with a formal group over R, I can define a homomorphism over R from G to a twisted version of G, where I pull back along this absolute Frobenius. So I can always pull back a formal group along a ring homomorphism, which, if I think of it as a functor of rings, means I'm pushing it forward. But geometrically, it's pulling back. This is called capital F. That's the relative Frobenius. What is this? Well, I write these in terms of their rings of functions. So here I have OG is the ring of functions of my formal group. Here I have a twisted version of the ring of functions of my formal group, where I shift by the absolute Frobenius. And the relative Frobenius is, in fact, the ring theoretic relative Frobenius. So it's the map that's the pth power map on this factor extended over this base change. So that's the absolute Frobenius. And that's a homomorphism of formal groups because this construction is functorial in rings. So it preserves the Hopf algebra structure on OG. So this is the Frobenius homomorphism. And I can do this to various powers. So if I like fp to the r, there's a similar construction. All right. So if I actually have a formal group over a field, so if G is over K and the characteristic of K is P, then any homomorphism of formal groups coming out of G factors through some power of Frobenius. So if I have a homomorphism over K, and let's say it's not the zero homomorphism, then there exists a unique factorization. Let's say I'll take G to G prime. I can factor it through some power of the relative Frobenius followed by an isomorphism of formal groups, G. Right. So we say that F has degree P to the R in this case. So all homomorphisms of formal groups over the field of characteristic P have a degree. And we can use this to construct an invariant of the formal group, which is the height. So the height of G is H, where H computes the degree of the power, the multiplication by P map on the formal group. So the degree is actually going to, of multiplication by P map will be some P to the H for some H. so H can take values in 1, 2, 3. It can also be infinite. Particularly the additive formal group is a group of infinite height in characteristic P. Okay. I'm going to concentrate on the case of finite height. So we understand a lot about, well, I guess it's pretty much we know a lot about the category of formal groups over fields of characteristic P. So here's a statement. If K is separably closed, any two formal groups, well, there exists a formal group of a given height, and any two formal groups are isomorphic if and only if they have the same height. So there exist formal groups of all heights over K, and height is a complete isomorphism invariant. Furthermore, if I pick a formal group over K of some given height, then the endomorphism ring of this formal group is understood. This is a pro-étale ring scheme, which is non-canonically isomorphic to a ring that looks like this. You've probably seen this formula. So this is the Witt ring associated to Fp to the H, adjoin a non-commuting generator S, which satisfies this identity. S commutes with scalars up to Frobenius. Okay. So this is a non-canonical isomorphism. If you're not over a separately closed field, you still know something about what goes on because the assignment of a field K to the category of formal groups satisfies Galois descent. So you can understand formal groups over more general fields of characteristic P using descent in a fairly straightforward way. All right. Let me get rid of this. So as probably everybody knows, the automorphisms of a formal group of height H are significant in topology, and that group, which is the group of units in that ring, is called the Morava stabilizer group. Let's see. All right. So I want to talk about deformations. So if I have formal groups over fields, that's nice. But I can extend to deformations of formal groups over rings that are schemes that are fat versions of a field. So I'm going to look at a ring R, which is going to be some kind of complete local ring, and whose residue field has characteristic P. So I can talk about formal groups over such a ring, and I'll say it's a deformation of a formal group of height K. Just say it's a deformation of height H if I take the formal group over R and I base change to the field. If this thing has, this is now a formal group over a field, if that actually has height H. So if I say I have a deformation, I think of that as over some neighborhood of a point, and this is the special fiber. So I have a family of formal groups parameterized by some fat neighborhood of spec of this field, and this is the special fiber. The special fiber has height H. Okay. So there's lots of ways in general to deform a formal group to some ring of this form. But there's one sort of important basic feature, which will stay as a proposition, which is that you can actually distinguish two homomorphisms between deformations exactly by what they do on the special fiber. So if I have two different homomorphisms, these are homomorphisms between deformations of height H formal groups, then they're equal if and only if the restrictions to the special fiber are equal. Because I'm not going to prove anything else in this talk, I'll prove this. Because we should prove something, right? It's very easy. Well, it's an induction argument, which is fairly easy to set up. This is a complete local ring. So, of course, you're going to do some induction by powers of the maximal ideal. So you reduce to the following situation, which is the sort of the induction step. You'll have a ring which has a maximal ideal. Maybe that has a smaller ideal R, such that m times I is 0. So in particular, I is a square 0 ideal. I might be something like m to the n minus 1. And R is a ring where m to the n is 0. Proceed up some tower by looking at this case. And you want to show in this case that, so if you have a homomorphism of formal groups over R, such that if I pass to R mod I, it's 0, the trivial homomorphism, then in fact F was the trivial homomorphism. So that's the induction step. Well, how do you do this? You write out your function in terms of local coordinates on these formal groups. So I'm going to suppose I have local coordinates, maybe x and y. F is going to be given by some series. It will have some leading non-zero term. Let's call it a, ax to the n plus higher degree. And the whole thing is in the ideal. Has coefficients in the ideal because I said that F reduced modulo the ideal I was the trivial homomorphism. That's the thing whose expansion is 0. Now, I'm going to use the following identity. Every formal group has a p-series. It's a multiplication by p map. And in this case, since I have a homomorphism, I must have this. F followed by multiplication by g is multiplication by p is multiplication by p following F. Sorry, I said that wrong. It's that identity. And so I'm going to write out this identity. Now, these are supposed to be deformations of a height h formal group. So I can write this. The p-series of g is going to look like, well, mod the maximal ideal m. This is some unit c, let's say, times x to the p to the h plus higher degree terms. And similarly for g prime. These are units. So what do? Well, you plug all this into this identity. I'm going to use the fact that this is true. So that means that even though I only wrote down the p-series modulo m, because I'm going to feed that into something whose coefficients contain an I can read off the answer in m. So if I identify the coefficients of the leading term, so this is going to be x to the n p to the h term. So on one hand, I get, well, I'll get the p-series. That involves c. But then I'm going to feed that into f. So I'm going to take a power of that times a. And that's going to be equal to, well, I'm going to start with f. But now I'm going to feed that into the p-series. And I'll have that times c prime. That's what you get if you match up the first terms. But a is in the ideal I. And I actually squares to 0. So I just told you that a times some unit up to some units, sorry, a up to some units is a power of a, which is more than the first power. So since a squared actually is equal to 0, and c is seen prior units, then a equals 0. So this leading term of f had to be 0. And so thereby extension.
R was like p-adix, then the whole thing would be
If R is the p-adix, so R could be something like z mod p to the n. That's sort of, I'm doing induction based on quotients of some ring. So if R is the p-adix, I would sort of climb up the tower.
But then your reduction, I mean, then it's all in the reduction step.
This is all in some sort of reduction step in some inductive argument. So imagine I have a homomorphism of probabilities over z mod p to the n. And I know that that homomorphism is a trivial mod p to the n minus 1. I want to show that it's actually trivial mod p to the n. So I'm climbing that tower.
So you still need this step even in the p-adic case.
You need it in the p-adic case. You have to climb. So you have to use this implement many times when you climb up some tower. This is just the key step in the argument. Huh?
You need it for all rings. It's not enough to show that for a fixed R.
Oh no, you need this for every ring of this type. All right.
The R in the proof is secretly R mod some power of n.
Yeah, secretly it's like R mod m to the n or something. This is why it's a good idea not to give proofs. People start asking questions. I've learned this. If you don't give a proof, nobody has any idea what question they're supposed to ask. You give them a proof, and uh-oh, they try to understand it, and then that's when the problem starts. Well, you know, it's true. All right. So this has a category of, let's see what I want to say. So I'm going to make a definition. So let's fix a height h formal group over a field. G0 over K, it will have some height h, which is finite. I used that this was, the h was finite, by the way. It's not what actually was involved in this proof. K here is going to be a perfect field of characteristic P. So given a formal group over R is a complete local ring, a G0 deformation structure, on R is the data, we'll call it I and alpha. I is an inclusion of fields of K into the residue field of R, and a choice of isomorphism of formal groups over R mod M. So on the one hand, I have G reduced to R mod M. It's special fiber. And on the other hand, I have I upper star of G0. G0 moved over to R mod M. This is an isomorphism of formal groups. I'll call that a deformation structure. And a triple consisting of G together with I and alpha of a deformation structure is what I'll call a deformation of G0 to R. I might use either kind of language. You can think of this in several ways. Here's one way to think about what this gives you. This gives you one way to think about it as some kind of functor. So if I have, I can actually define a set. Let's call this D sub G0 of G mod R. This is the set of G0 deformation structures on the formal group G over R. And this construction is functorial on formal groups over R and isomorphisms between them. So given an isomorphism of formal groups, I get a function, which I'll call f lower shriek, from the deformation set of G mod 0 R, the set of structures on G prime. G0 is understood. And how do you do that? Well, it's pretty easy. You have an isomorphism. It reduces to something on the special fiber. And in each case, well, in the first case, I have a deformation, which is an isomorphism. I guess it goes this way. And I need to somehow produce another deformation for this. And so the rule is you just use the same I. And then, well, it's a diagram of isomorphism. So you put in whatever's here. So this thing is F restricted to the special fiber. And this alpha prime is just the thing that makes the diagram commute, whatever that is. F mod M inverse followed by alpha. Right. Okay. So one way to think about this is that this is a deformation structure is something you can attach to a formal group over R, and you can push it forward along an isomorphism. A different way you can think about this is to think about deformations So if I just happen to give myself two deformations of G0, the proposition I showed earlier tells you something. It tells you that there's at most one way to have a homomorphism from G to G prime that's compatible with the deformation. Compatible means I'd like to have a homomorphism such that on the special fiber, if I look at this, it makes this diagram commute. So it's the same picture, but now I'm thinking of myself as giving alpha and alpha prime and asking for an F. So there it exists at most one F from G to G prime compatible with the given deformations. So if you think about it this way, this tells you that a deformation doesn't really have any automorphisms other than the identity, at least ones that are compatible with the deformation. And if I have two different deformations, the property of there exists an isomorphism between them compatible with deformations is a kind of relation on isomorphism classes. All right. That relation is sometimes called star isomorphism. So the starting point is the theorem of Lubin and Tate. The functor that associates to R the set of deformations, isomorphism classes of deformations of G0 is representable. Theorem. Lubin and Tate. I'm good at breaking chalk. All right. So the functor that takes a complete local ring and gives me isomorphism classes, or usually people say star isomorphism classes of G0 deformations to R is represented by a complete local ring, a ring, I'll call it either A0, or if I want to specify the formal group I'm deforming from, AG0. So that's in the category of complete local rings and continuous homomorphisms. And furthermore, we can say what the structure of this ring. This is isomorphic to the p-adic fit ring on K adjoining a bunch of power series variables, H minus one of them, where H is the height of G0. Okay. Well, so it represents a functor, so it comes with a universal example. So the identity map on A0 classifies the universal deformation. So G univ over A0. So the residue field of A0 is just K, and then I is the isomorphism. K to A0 mod M. And alpha is given. Well, it's part of the structure. I am not going to explain this theorem. So the Witt vectors, this is just a way to produce an unramified extension of ZP whose residue field is your given field. That's its role. So in particular, if you don't like it, just imagine that K is FP, which has the other nice feature that then you don't have to worry about this I because it's always unique. And then with this case, this would just be the p-adics. Okay. So this part here is actually given entirely to deal with the fact that I decided to put an I here. I wanted to have as part of my data some map of fields, and that I can actually classify lifts of that to R using this WK. So that's sort of a minor feature of this construction, which I could have left out, and possibly should have. All right. So this classifies deformations up to isomorphism. You can also think of it, by the way, as classifying deformation structures. So, so I had this set of deformation structures, G0 deformation structures on a given formal group G. So this is G0 deformation structures on G. And that is in bijective correspondence with the set of continuous homomorphisms from A0 to R, which have the property that under that homomorphism, the universal deformation pulls back to something isomorphic to G. So this is isomorphic to G. This is just as formal groups, not as a deformation. So I'm not worried about the deformation structure. That's sort of taken into account by this. Once you give yourself a phi and an isomorphism, that automatically provides G with the structure of a deformation, sort of by abstract nonsense. All right. Yeah. Well, why the p-adics show up? So I'm working. So I started without. Okay. So first of all, just assume that K is FP, and then this is the p-adics. My rings that I'm deforming to have to have a residue field FP, but they're complete, so they could include the p-adics. So the general kind of ring I'm deforming to will always, in fact, be an algebra over the p-adics, because they're complete local rings with residue field, like field of characteristic P. So if I want to have a universal example, it can't just be a K algebra. It has to be at least a ZP algebra. I actually need it to be a WK. I need to actually have this unramified extension of ZP because the residue field has to at least contain K. So this is just some algebraic stuff to make that happen. It's relatively unimportant for what I'm doing. Just assume that's ZP. All right. So the observation I want to make is if I think of this as representing something about deformation structures, then there's an action of the automorphism group of the original formal group G0 over K. This actually acts in a canonical way on the set of deformation structures for any G. The idea is that if I have an automorphism, and then if I take a deformation structure, well, alpha is a map essentially between G and G0, or G reduced to its special fiber, the special fiber of G and G0. And so I can compose alpha with some automorphism of G0. That defines an action. So this is an action of this group, which is the Morava stabilizer group, if I choose G0 suitably, on this set. And this actually gives an action of the Morava stabilizer group on the ring A0. All right. So far, so good. So of course, the punchline is going to, well, one punchline is going to be is that there's going to be a cohomology theory, even periodic cohomology theory, whose pi 0 is A0, and whose formal group is the universal deformation. That's Morava E theory associated to this formal group G0. But let me say that a little bit later. Let's point out a little bit more that I have going on here. Let's see, it's still up on the other board. So let me bring up the other board. I pointed out that I could push forward a deformation structure along an isomorphism between formal groups over R. But I can extend this operation a little bit. So let's see how I'm going to do that. Let's keep this. Let's suppose I have a homomorphism of formal groups over R. This is over R. I'm going to suppose this is a homomorphism. I'll suppose that it's not 0. I'm going to call this an isogeny. Let me just call it homomorphism that's not 0. Come back to that later. Okay. So I'd like to have a way to push forward a deformation structure along a homomorphism. So, well, I can do this. I can look at, let me erase part of this diagram here. I'll suppose I've given myself, let's erase this. So, let's erase this even. I start with a deformation structure for G, I alpha, and I'd like to push it over to the other formal group G prime. How do I do that? Well, start with my homomorphism. It gives me a homomorphism of formal groups over the field R mod M. Now, I started out by telling you a fact about homomorphisms of formal groups over a field, which is that they factor canonically through a power of the relative Frobenius. And that's what happens here. In fact, let's see, how do I want to say this? Let's actually think about this composite. That's a homomorphism of some degree. I can factor that canonically through a power of the relative Frobenius. So I'll write sigma to the R star of I star of G0. And this map is going to be F to the R, that relative Frobenius homomorphism. And that factorization is through an isomorphism. I'll make the isomorphism point the opposite way than I had in my original example, but it's still an isomorphism. So there exists a unique there exists a unique R and isomorphism alpha prime making the diagram commute. So that's what I'm going to do. I'm going to push this forward to I composed with sigma to the R and alpha prime. So this is a recipe for pushing forward a deformation structure along an isogeny. I'm going to use this word. I'm going to end up using this word. I'll call this an isogeny, as well as a homomorphism. It's basically a synonym the way I'm using it now. So the idea is you factor the deformation through canonically through some power Frobenius. Okay. So this is sort of extra structure. Let me say a little bit more about this. So I pointed out that there's a universal example of a deformation that lives over this ring A0. Oh. Doesn't work so well. All right. And actually, I told you this story about how you could think about deformations in terms of you have two different deformations of G0, and you have a relation which says whether or not those two things are isomorphic as deformations. So I can convert this story into a similar story about a relation between two deformations. So the proposition I told you originally says the following. Given two deformations, G I alpha and G prime I prime alpha prime of G0 to R, there exists at most one F, a homomorphism from G to G prime, such that it's compatible with the relative Frobenius F to the R on G0. And that's exactly in the sense of what's on the board on the right-hand side, that some diagram commutes. I should have said here, no, that's exactly right. There's at most one of these for a given R. So you can ask if you have two different deformations whether or not they're related by an isogeny that is a deformation of F to the R, that is a deformation of the relative Frobenius isogeny on the G0. Either they are or they aren't. This question is also represented by a ring. And this ring, so this problem, is also represented by a ring. Which I'll call A sub R, or maybe more generally A sub G0 F to the R.
This question now we made equivalence classes.
Yeah. let me write down the ring, and then I'll explain what it's representing. It's going to work better. So the idea is this ring is actually going to be isomorphic to a quotient of the tensor product of two copies of A0. I've completed it because these are supposed to be complete by some ideal that depends on the situation. So the idea is if you have two different deformations, those are each represented by maps from A0, then the relation, are those things related by a deformation of F to the R, is actually a relation on that pair. And it's a closed relation. It's defined by equations which generate an ideal. Okay, so that's what I mean by it's the universal example. Right. And it does carry, this carries. So there are two different maps, notice, from A0 into this ring, because it's a quotient of the tensor product. I'll call them S and T. And this ring, AR, carries the universal example of an isogeny which deforms Frobenius. Let's write the example. It's S star of G univ to T star G univ. Universal example of an isogeny which deforms G, F to the R. Okay. All right, so I've set up a bunch of stuff about formal groups. And in what comes next, I want to show how this relates to a cohomology theory, which is marathi E theory. Are there questions before I go on? I'll tell you something. I don't know. I mean, sure. I guess I could just say yes, because I'm sure to say something about the structure. Is there something in particular you have in mind? All right, so far I haven't told you anything other than it's some quotient. And this isn't actually very useful on its own until you can say something else about it, obviously. I'll give some examples later on. One more point about this, which I should point out, because if you go read the literature on this, this is the way it may be said. If you can rephrase this problem slightly differently, where you fix the deformation G, and you ask about all possible ways to have an isogeny with source G, which is a deformation of F to the R. And any such isogeny has a kernel, which is a finite subgroup scheme of the formal group G. And one way you can describe this ring, an equivalent way to what I said, is that AR is precisely the ring that classifies a deformation G, I, alpha together with a finite subgroup of G of degree P to the R. That subgroup is the kernel of this universal example of an isogeny that deforms F to the R. So that's a different language for the same thing. But so this is sometimes also called some letter, A or O or whatever you like, sub P to the R. It classifies subgroups of a deformation. Yep. All right. Anyway, I'm going to break here because I'm supposed to break at some point. This makes sense. And then we'll come back. So, let's see. So we have cohomology theories associated to formal groups of the type I'm talking about. So, for instance, if I have a formal group of height h over a field, there's an even periodic cohomology theory, which I might call k sub g0 sub little k. There are too many k's in topology, as you know. This is not K theory, but this is what's sometimes called the even periodic marathi K theory. So the idea is it's an even periodic ring whose formal group is exactly G0. And pi 0 of this thing. This is field K, over which that group's defined. And this is an even periodic ring spectrum in the sense I described last time, with some caveats, like I think I wanted them to be homotopy commutative always, and these are actually never homotopy commutative if you're in characteristic 2, which is sort of an indicator that stuff doesn't work as nicely as you want. It does turn out to be, by a theorem of Robinson and Baker, that this K admits an A infinity ring structure, and these can be classified fairly explicitly by work of Engelweit. However, this thing cannot admit any commutative S-algebra structure. It's not a structured commutative ring. So, well, that's unfortunate. It's related to Morava K theory, which is Kn, and this is kind of an irreducible summand of any one of these Ks, as long as the height is h. I guess this would be kh in this case. And I mention that because at some point I'm going to have to trot out the notion of kh local homotopy theory, and just so you're thinking about kh. All right. So the object I want is the one associated to this universal deformation, and that's called Morava E theory. So given G0 of height h, there's something called E. Let's say G0 over K. This is Morava E theory. Both of these were introduced by Morava. It's also even periodic, and it's associated to the universal deformation. So pi 0 of E, let's just call it E, is E0, and the formal group is the universal deformation of G0, which I call G unit. Okay. So this is in some sense this is easier to construct than the K version because it's a Landweber-exact cohomology theory. So you can plug it into some machine to construct it very easily. But it's even better because of the theorem of Gorse, Hopkins, and Miller, which is that En, or E rather, there's no N here. E, any of these E's, E, so G0 over K, admits an essentially unique commutative S-algebra structure. Actually, the construction of the Morava E theories is entirely functorial. For any such formal group, you get an associated E theory, which lives in, this is a formal group over K of finite height, and you get a commutative S-algebra here. And this is functorial with respect to isomorphisms of such formal groups. Finite height and isomorphisms. This is a functor. Okay. Right. Well, this is awesome. So, as I told you last time, commutative S-algebras give you a way to construct power operations. So let me just tell you what I'm going to tell you sort of some features of that structure. So remember, if I have a space X, then this means in particular I get an operation from the E cohomology of X to the E cohomology of B sigma M. And this is defined by refinement of the mth power of the cut product in this theory E, which exists because it's a commutative S-algebra. Okay. Now, I pointed out, at least in the example of the K theory example I gave last time, this map is multiplicative always. It's a formal property because it's built from multiplication. So it's multiplicative. It is not, however, additive, which is awkward because it's hard to deal with things that aren't linear. But there's a precise understanding of how it fails to be additive. So here's the formula that's the replacement for additivity. So if I apply this operation to a sum what is this? Well, it's a sum over I plus j equals m. People see. All right. Well, I can take pi of a. I can multiply that by pj of b. So this involves sigma I. This involves sigma j. But sigma I times sigma j is a subgroup of sigma m by sort of permuting two different blocks. And so this product is going to be the one that lands in E b sigma I x times b sigma I times sigma j. But that's still sort of in the wrong place. I need to be in b sigma m. And the answer is that you transfer up. So I transfer from sigma I times sigma j up to sigma m. This is nothing special about Morava ether. This is true for any such power operation coming from a commutative S algebra. It's also true in the K-theory example, which was an equivariant example that I described last time. I just didn't end up writing it out. Where transfer, in that case, was actually given by an induced representation. OK. So we understand how this fails to be additive. And the idea is that we can just mod out by that failure. And then we're good. So what I'll do is I'll consider an ideal generated by all transfers from all proper subgroups of that form. So all ideals are probably going to be called I or something. There's going to be a lot of them. But they're all of this form. So I is going to be the sum of the images of the transfers. That's right here, m minus I, up to sigma m from the cohomology of x times the subgroup up to x times b sigma m. And this is over proper things. So I is strictly between 0 and m. And this is an ideal inside that target. It's called the transfer ideal. We call it I sub tr. So what I do is I consider my power operation, and I project down to the quotient, which is this target, divided by the transfer ideal. And this is exactly set up to kill the middle terms in that sum. It's basically a binomial expansion somehow, really. And so I just have the terms at the end, which are the ones I want. So this thing is additive and multiplicative. It's a ring homomorphism.
One question. Clearly, this is enough to get this additive, but wouldn't one expect to get something more computable if you did the transfers of all proper subgroups and they're not necessarily contained in these?
They're not necessarily contained in these. Well, you don't want to do all, if you choose the wrong subgroups, you'll kill your thing entirely. This is a symmetric group. This turns out to be the right thing to do for symmetric groups. It just is.
Intuition comes from character theory. Character theory tells you this is killing off exactly what you want to get rid of.
I guess. That's one way to think of it.
So you're telling me for this example, it's the right thing to do?
Actually, for any example, it's the right thing to do. So far, I haven't really done anything about Morava E theory. This is always the right thing to do if you have a power operation. Is consider what happens if you mod out by this ideal. It's sort of the best thing you can do if you want to get a ring homomorphism, which you probably want at some point, just because they're nice. Okay. All right. So this thing is a ring homomorphism. And I haven't really used any property of Morava E theory at all. In this case, I have a little bit more going for me, which is that I can describe this. So it turns out that the Morava E theory of symmetric groups is a finitely generated free module over the coefficients. So I can therefore apply a kind of Qunut theorem in this setting. This is actually isomorphic to the ecohomology of x tensored over the ecohomology of a point of the ecohomology of b sigma m. And so this also projects to something, which is the ecohomology of x tensor over pi 0 v, e0 b sigma m, and I can divide out just by the analog of the transfer ideal, but just for the cohomology of B sigma m. And these actually turn out to be isomorphic too. So this is something that's special for marathi E theory, and why this is a really good setting to think about power operations, because you have this fact. In general, for some general theory, this could be a very difficult object to describe. But this means you have some hope of describing this in a way that sort of doesn't really depend on x, which is the problem you're worried about. OK, cool. So we have an operation. And I should have pointed out at some point, because E is a p-local theory, if m isn't a power of p, then this transfer kills everything. There's a p-CeLO subgroup inside one of these subgroups, unless m is a power of p. So this guy is 0 unless m is p to the r. So we're only going to see things for p to the r. One other thing I pointed out about power operations is that they refine the usual p-th power. So for instance, we can restrict from the e-cohomology of a symmetric group to the e-cohomology of a point. So this is just E0 of x. This is just a restriction. And the observation is that this thing is going to be an mth power map, which I've decided is going to have to be a p to the rth power map. That's not a ring homomorphism, because it's just not. But if I pass to the quotient, let's see, how do I want to say this? Let's just say that this ideal I transfer is itself contained in sort of, I'm not going to say this right. Well, we can build this diagram, let's just say. So E theory, remember, is the cohomology theory whose coefficient ring in dimension 0 is A0, the universal ring for deformations. And this thing is actually the ground field. This composite from E0 to this quotient of E0 of x mod the maximal ideal is also the p-th power map. This is just passing to this quotient. This is a ring homomorphism. So whatever this ring homomorphism is, it's a lift of the p to the rth power map. That's a different reason why m has to be a power of p, because there is no such ring homomorphism otherwise. Mth power map isn't usually a ring homomorphism. All right, so you might ask, what map is this? You might in particular ask, let's take x to be BU1. So then, of course, E of BU1 is the function ring for the formal group of E, which is also the universal deformation. And so somehow I've produced out of this a power operation. If I plug in U1, this goes to some tensor product of this gadget with this other ring, which I somehow committed myself to writing out every time I talk about it. So this is the function ring tensored up by whatever goes there. And so you can ask, what is this ring homomorphism? Oh, I should say a little bit more. After all, this is a natural operation. This is the ring of functions on a formal group. So it has a co-multiplication that gives the group structure on the formal group. And this is natural with respect to that co-multiplication. In other words, this is going to define a map of formal groups from this formal group into something over here. And the answer is that this thing defines exactly the thing I was talking about last time, the universal deformation of f to the r. So this is a theorem of Strickland. Let me state this now more carefully. So the key theorem is to identify what this is. And it is the universal example of the thing it's an example of. Right. Yeah. Right. So here's Strickland's theorem. So there's an isomorphism I called this ring A sub r before. This was this ring that classifies the universal deformation of f to the r. This is exactly this quotient. So in this case, it's a symmetric group p sub p to the r. Okay. Furthermore, evaluation at x equals bu1 gives you the universal deformation of fp to the r. So let me just spell out how that appears. So let's write it like this. So remember, AR was supposed to come with two different maps, which were source and target. This map, this is the e-cohomology of a point. This is this quotient of the e-cohomologies sigma p to the r mod an ideal. And this is just the usual one induced by the map from the classifying space to a point. So this one just comes from topology. So this is restriction. So it's pi upper star. What's this map? T is completely different. It's the map that comes from the fact that I have power operations, which I called P overline P sub P to the R. And I can apply that in a case where x is a point. That's T. And then the universal lift, or the universal deformation of f to the r, which I wrote as s star of g univ, t star g univ, defined over this ring, which is isomorphic to this, is represented by, well, it's effectively represented by what happens if I plug in bu1 for x. Let me actually write this out, just because it's it helps to see it done this way. So the idea is that I have the e-cohomology. I'm going to take x is going to be bu1 in here. But let me write it a little bit more generally. I have e0 of x. I have this reduced power operation. It goes to e0 of x tensor e0 of a point. Quotient sigma p to the k mod I. I'm calling this r. That receives a map from the e-cohomology of a point. This is also pi upper star. And this is p upper p to the r for a point. And this is the same ring. Probably should have figured out how to abbreviate this. This is also pi upper star, but now it's on the x factor rather than on the symmetric group factor. Okay, well, these are all maps of rings, so there's a map from the push-out of these things to this guy. The push-out is the cohomology of x tensored over the usual inclusion of the scalars along this map that I called T. So I can rewrite this as a map. I take e0 of x, tensor over e0 of a point, which is also called a0, so I'll write it like that, with ar. But I do this along the homomorphism T, the target homomorphism, which is this. And that's that push out, and that's going to map to this gadget, which is e0 of x tensored over a0 with also ar. But now this tensor product is formed using the usual one that you would do if you didn't know about power operations, and that's S. And that's what this map is. I'm going to call this, I don't know, I'll call it psi sub r. So that's the universal deformation. And if I plug in x, bu1 for x, that universal deformation is represented by a ring map, which is this. So you plug in. This is represented by this when x is bu1. That's the theorem of Strickland. You go read his paper. It's not how he says it. There's a reason he didn't. He didn't want to actually use the fact that Marathi E-theory was a commutative S algebra, because this was happening circa 1996 or whatever, and that was still sort of, nobody was really sure if that was sort of a solid theorem, and maybe you need to use this stuff to prove it. So he talks about AR in terms of the ring classifying subgroups, as I sort of mentioned at the end of the first half. So that's how you read about it in his paper. And it's a fairly complex proof. There are two elements that well, there's one element that I should single out that's topological, which is also an interesting property. So I just defined this quotient of the cohomology of B sigma p to the r. I said the cohomology of E sigma p to the r, the symmetric group, was a free module. It's actually true that this quotient is also a free module over E0. Specifically, a free module with respect to this ring homomorphism called S. That's a non-trivial fact, and you have to extract that somehow from topology. It derives in his proof ultimately from a fact about, something like the BP Hopf ring of QS naught due to Kashwa bar or something like that, if I remember correctly. So there's some input that you have to get that sort of tells you that that thing's a free module. In fact, so that we can have as a conclusion here that S, this thing presents AR as a finite free A0 module. And you can figure out what the rank is. It's some number you can compute. Okay. T is also of the same sort. Okay. What else should I say? The other part of his argument is, well, you have to figure out why this thing carries the universal example of a subgroup. And there are a number of ideas that go into it. One of which Nat sort of alluded to, is that you can use character theory to get control of this. So a way you study the cohomology of a symmetric group is you restrict to abelian subgroups. The particular example that's important here are abelian subgroups that act transitively on the set that the symmetric group acts on. It's transitive subgroups. There's actually a geometric interpretation of those rings, the cohomology of such abelian subgroups, modulo a transfer ideal, and that's in terms of something called Drinfeld level structures. So you can get sort of restrictions on that. That's sort of somehow you can understand a little bit more directly. You can get your hands on, and that puts some constraints on what this thing could be. And that's another part of his argument. And there's actually also a fairly complicated induction that you have to do to get the whole thing. I've never really figured out how to explain the argument, even when I could remember how it went. And I don't remember anymore. So I should mention that Tomer Schlank and Nat Stapleton have a simplification of that part of the argument using a completely different idea, which uses some kind of character theory to reduce the problem of identifying this as carrying the universal subgroup to something that happens in height 1. So it's a different idea, so there's a different approach on it. Okay. So this is the input to some theory of power operations. All right, so what should I say in my remaining time? So let me sort of set up sort of what this gives you. So I've defined some operations. As I've set it up, I've thought of it as something that acts on cohomology, which is correct. But really the proper context are K and local commutative S algebras. Or maybe I should say K and local commutative E algebras. So, what? What? What?
Water on the spine.
Yeah, I need some. If I use too much water, then it just gets damp, and then so I don't want to use too much. Right. I'm sorry. I'm sure I'm doing a horrible job at this. But. All right. So if I have an E algebra spectrum, a commutative E algebra, I actually get power operations on such gadgets. This will go from the pi 0 of R. You might wonder, by the way, why I'm only ever doing pi 0 and not pi n, in the interest of time. There is you can give the analog of this story for any degree. It's a little bit more complicated. So that thing on the right is the function ring. So this is the function spectrum from the suspension of B sigma m to R, which is also a commutative S algebra. And so the power operation really defines a function like this. E is marathi E theory, some fixed marathi E theory. All right. Now, I have to pull out the word Kn local if R is not merely commutative algebra, but if it's also Kn local.
So you're putting a bar on the P, but you don't have to divide it out by anything.
Yeah, you're right. So let's not divide out by anything. Let's not put the bar in. Great. If R is P local, or sorry, it's Kn local, then well, you have a kind of, you can apply the Qunut theorem in this case. So R is an E algebra, so I can tensor over E with the E-valued cochains of the symmetric group, and that comes with a natural map to the R-valued cochains of the symmetric group. In general, there's no reason to think that these are, now I'm confused. Yeah, there's no reason to think that these are equivalent, but if you know R is Kn local, then that ensures that they are, and this is a weak equivalence. And, well, this spectrum is a free E module. So, in fact, the homotopy groups of the thing that's the target, say pi 0, are actually going to be the homotopy groups of R tensor over E0 with E0 b sigma m. Okay, so this is sort of the correct context in which you can apply these power operations. What I was doing the case where R was itself just the cochains on some space. Let's see. I mean, I can definitely have I can certainly have an E, let's see, what's an example? Yeah, R could be rational. That's a good example. It could be E tensor Q. And then the actual sigma m cohomology of that will just be, you won't see anything. So you definitely need to have something here to understand this object. This object is sort of always sort of what you want it to be. It always looks like this because this thing's a free E module. So this left-hand side always gives you this formula, but this operation takes values in this guy. Yes, because if the R is itself, if it's local, then any function spectrum is also local. So that's all I really need. The smash product isn't, but in this case it is, because that's a finite free E module. It sort of just works out for you. But you need something, which is sort of makes it awkward. So what this gives you is operations on pi 0 of such a gadget. So let's just see. I just want to sort of summarize what this looks like. So let's take such an R, and let's look at B, which will be pi 0 of R. So what I've told you is that for each ring R, you get a ring homomorphism from B to B tensor a suitable quotient of the cohomology of the symmetric group. So I'll write this as B tensor over A0 with AR. And I'll decorate this tensor with an S, just to remind me that that's how I'm forming that tensor product. Sometimes I actually put the T out on the other side, because this is a map of A0 algebras. But this is an A0 algebra because it's an E algebra. The spectrum's an E algebra, so it's a module over pi 0 of E. This thing gets to be an E0 algebra using the structure that comes in on the right using this map T. This is a map of A0 algebras. So this is the algebraic structure that comes out of these power operations. And they fit together. This is what you get. You get commutative diagrams which say the thing that you expect. This looks kind of like a coaction, and there's a co-associativity. So I have B going by C psi R to B tensor AR. And then I have identity tensor psi R prime that goes to B tensor AR tensor AR prime. And that turns out to be the same as applying psi R plus R prime. I'm not sure if I'm using upper or lower indices, so I'll do there. And this map on the bottom I'll call this identity tensor mu. This is associated to a map that classifies what happens if you compose two isogenies. So mu, it corresponds to composing isogenies. I should have decorated this. All the tensors are over A0, and then there are superscripts telling you which ring structure you use. So that's S, ST, S, S. All right, this commutes for all R and R prime. Sorry. Okay. So there's a name for a ring that has this kind of structure. Well, there are many names. I always come up with a different name every time I give a talk because I can't decide on the name. A good name is we say that B is equipped with descent for isogenies. That's the structure that power operations give you, or a structure it gives you, descent for isogenies. So it basically looks like I've said that B is some co-module for some coalgebra. In fact, this coalgebra is some kind, more or less a bialgebra. Only it's sort of a bialgebroid because there's a left and a right unit. And I can't say it's a Hopf algebroid because it doesn't have an involution. It's a category. It represents some kind of category, not some kind of groupoid. If you're familiar with the language of Hopf algebroids, that's how it differs. There's a little bit more, though. And I made this point, of course, last time when I gave the example of K-theory. I pointed out that there was an operation you got there satisfied a congruence. And that happens here, too. So let's see. What shall I say? Oh, I was going to say something else. Okay, we'll just say it has descent for isogenies. I want to focus a little bit on the case of psi1. That's associated to the symmetric group sigma p. So what I'm looking at are operations which take place, whose values are in some ring that involves this quotient ring, A1. So I'm going to take whatever's here, tensor it with, the homotopy of R, and then my operation goes from pi 0 of R into pi 0 of R tensor this guy. But psi1 is just going to be the thing that lands in this quotient. So the operation psi1 comes with a lift to some bigger ring. This would be the map. This is not going to be very clear the way I said it. This would be the P sub P, capital P sub P. Now, you should think of this as extra data. And here's what this is doing for you. So here, I have a restriction to the point. This is the topological map, restriction along the base. Actually, I should call this J upper star. This is restriction along the base point inclusion of the point into B sigma P. And if I mod out by, if I restrict to the base point, and then also mod out by the image of the transfer ideal, you can convince yourself that this is really just the coefficient ring mod P, E0 mod P. I have a commutative square like this. This is also induced by restriction to the base point. This square turns out to be a pullback square of rings, okay, as well as a push-out square of rings. I've distinguished here a map. This ring is A0 mod P. This is A1. So somehow I've produced a map from A1 to A0 mod P. Let me call this can. What is this map can? This classifies something geometric. This is universal for deformations of F. This is universal for deformations of the original formal group G0, which happen to live over a ring of characteristic P. That's what it means to say I'm looking at A0 mod P. This is going to look like K join some power series variables. there's a canonical example of a deformation of Frobenius to a ring of characteristic P. That canonical example is the Frobenius homomorphism itself. Frobenius, for a formal group, is defined over any ring which contains Fp. It doesn't have to be over a field. I'm looking at deformations. Well, clearly F is going to be a deformation of Frobenius on the special fiber, which is defined over a field. So that's a canonical choice of deformation. It's not the only choice. There are many deformations to rings of this type, but it's a canonical one. So my operation, which somehow wants to live in here, lifts to something here, and this is a pullback square. So this is telling me something about my operation. And what it tells me is the following. This is where I didn't set things up properly. This tells me that I have a Frobenius congruence. All right, how do I want to say this? Let's say it like this. So I'm going to translate what I just said into something in terms of that language. So I think I pointed out that I have some descent for isogenies, and I didn't give a categorical description of it. So let's say I have one of this B with descent for isogenies. So that's the data that's all the way up there, all these psi r's and satisfying those commutative squares. What this means is that if I have a deformation, maybe I'll think of it as a G with a deformation structure, then I can associate to that a ring, which I'll call B underline sub r of this data. And this is just what happens if I take B, which is an A0 algebra by its nature, and I tensor along the homomorphism to R, which classifies the deformation. So I'll put that up there just to tell you that this homomorphism from A0 to R is classifying some deformation. But now, if I have a map between isogenies, then there's going to be a corresponding map. This is B tensor A0 R. This is G prime, etc. There's going to be an induced map, like this. How is this map defined? I'll think of this as induced by R. Let's call it F shriek or something. How is that defined? It's defined using psi r. Defined, F shriek, is defined using. So I had this map psi r from B to B tensor over AR, decorated by S. But I could tensor that up to a map from B tensor over AR with T. So I'll call this psi r twiddle. I've just base changed up. This is defined using this operation, which is implicit in having a psi r, and the map from AR into capital R, which classifies the isogeny, F. Let me not sort of spell all that out. Just put that together. So I get some kind of construction which associates to any deformation a ring, and to any isogeny between deformations, a homomorphism of rings. So I did this over a fixed ring R. That's why I call it B sub R. But I could also change the ring. And I could pull back along ring homomorphisms. These are supposed to be compatible with that structure as well, because it's all given on some universal guy anyway. Okay. And so now I can say what the Frobenius thing is. So there's a particular example of a map between deformations. I kind of wrote it out here. It's a Frobenius map. And so this congruence, this additional observation, is that if I take B sub r for this R, which is characteristic P, and apply this to the Frobenius homomorphism, let's see, sigma star G, I compose sigma, I think this is alpha prime. This map is a map between rings. This ring is actually just BR of the original guy twisted by the absolute Frobenius. The existence of this lift to this object tells you exactly that this thing is itself a relative Frobenius of rings. So the difference, I'm not sure how clear this came out, probably not very, but the key thing is that the difference between having something that lands in here, which is the algebraic thing I told you about, and something that lands up here is a congruence, which you can express in terms of sort of universal examples by the idea that if you push forward stuff along Frobenius, and I probably should say pull back here. Oh well. The reason I should say pull back is that I got the variance wrong. If you trace through with this, how this works, the map goes that way. There it is. That's much better. If you trace through this thing, pulling back along Frobenius is exactly has to have the effect of on the rings, has to be represented on rings by the Frobenius map on rings. Yep.
Okay. If I can describe you making the point that this is analogous to what I would usually call a relation in the K-theory example, which really meant
Yeah, I was going to do that. I was going to do that example next because that makes it much clearer. All right. So this is an additional piece of information that this has. Let me pass to the examples in the short time I have left. All right. So the first example is a height 1 formal group. And an example of this, of course, is given by the multiplicative group. So if you remember the structure of A0, it's a power series ring on h minus 1 variables. So when h is 1, that means no variables. Example. G0, let's say over Fp, is the multiplicative group. That's height 1 for any prime. The universal deformation therefore lives, should be a P, over the P-adix. And in fact, you can take the universal deformation of the multiplicative group to be the multiplicative group, just over the P-adix. So G univ is also the multiplicative group, conveniently. Now you can ask, what are these rings AR? Well, this is a quotient of a tensor product of A0 with E0, so there's not much room here. These are also all, in fact, ZP. So this is often, you can say this in terms of the formal group, maybe more concisely. The multiplicative group has exactly one subgroup of degree p to the r for any r. So there's nothing to classify if you're classifying subgroups. Or a different way to say it, you can canonically lift Frobenius, or uniquely lift Frobenius is what I'm saying. So the associated Marathi E theory is P completed K theory. I've given you a collection of operations for every R, but I said there's some compatibility when they compose. So in this case, you only need the first one. So I have an operation. Let's take a B. We have an operation on B. So B is maybe the homotopy of a K1 local K algebra. I have an operation called psi1 from B to B tensor over A0, A1. This is none other than just B again. This is exactly what in the previous lecture would have been the P-Adams operation. It is that. The Frobenius congruence in this case takes the simple form, which was also in the last lecture, which says that if I take this Adams operation, mod P, it's actually the P-power map. So all this complicated stuff is just a fancy way of writing this down in the case of K-theory. So that's pretty easy. So one additional point. In the previous lecture, I made some point about how the fact that not only do you have a congruence, it was witnessed by some funny operation called theta p, which was sort of an explicit way to realize that congruence. And that's in this story up here, too. The fact that I have a lift to the E theory of B sigma p, in this case K theory, you can find in there another operation, which is theta p. So it's actually in this story. So in fact, it turns out that the operation that
Were you just saying this F upper shriek is secretly the theta?
this F upper shriek is just something that you have in general. The fact that I did not say very well here, that there's a condition on this F upper shriek that it always has to be the relative Frobenius on rings. That fact is exactly this fact. Whatever funny fact here that I didn't say very well is precisely stating some congruence, which in the K-theory example is just this. Okay? All right. So in fact, if R is a K1 local commutative S algebra, commutative K algebra, then pi 0 of R is a theta p ring in exactly the sense I described last time. And in fact, that in some sense describes all possible operations on that, the homotopy of that object. So this is sort of been, this fact, which is sort of a fact that you can really use, and has been used by many people. So Garrett is an expert on this guy. All right, so anyway, there's an example. Let me do briefly a height 2 example where I'll just write out what the answer looks like, because that's, I think, more convincing than telling you formal stuff. All right, so here's the height 2 case. So of course, I care about this because there are elliptic curves whose formal groups have height 2. Those are the supersingular curves. So there's a particular elliptic curve over, let's say, F2, to be precise. This is an elliptic curve. Its affine equation is y squared plus y equals x cubed. And this is what's called a supersingular curve, which means exactly that the formal completion of this curve is a formal group of height 2 over F2. So I can consider the Maravi E theory of this formal group. Now it turns out that, so the Maravi E theory carries the universal deformation of the formal group, but by something called the Sayre-Tate theorem, it also carries the universal deformation of the elliptic curve. So in fact, it's an example of an elliptic spectrum. I want to give this example, and then I'll be done, because I'm running out of time. I'll give it using formulas, because that's nice. Right. So let's see how this works. So we get a spectrum called E, which is the Maravi E theory associated to the universal deformation, or sorry, associated to that formal group, whose formal group is the universal deformation. So A0, which is pi 0 of the spectrum, is, in this case, just ZP adjoin a single power series variable, which I'll call A. P is 2. All right. I'll tell you what A1 is. A1 is Z2. Well, let's just say it's A0. Adjoin a new variable called D, divided by the relation D cubed minus AD minus 2. So this carries two different maps from A0 called S and T. S is the obvious one. S sends A to A, if you like. A0 is the non-obvious, or T rather is the non-obvious one. It sends A to A prime. A prime is some polynomial that I can write down. It's A squared plus 3D minus AD squared. Okay. So if I have a K2 local, because we're height 2, ring, commutative S algebra, commutative E algebra, then I obtain an operation called psi1. So if B is pi 0 of R, it's a K2 local commutative E algebra, sigma E is this, then I get a power operation, which I would call psi1 in this formalism, like this, of course. Right. This comes with, this satisfies the Frobenius congruence. So I can pass to the quotient, or this is actually A0 mod P. This is identity tensor can. And this ring is really just B mod P. This satisfies the Frobenius congruence, just as the composite of psi1 with this projection is precisely the Pth power map on the ring. That's all it says. All that nonsense was just saying that some map is a Pth power map. That's what I should have said. It's much easier to say. Now you might ask, okay, there are higher psis. And in this case, because there's this fancy coalgebra structure, there's a bunch of relations I have to satisfy. So the surprising thing here is that first of all, I only need to produce this. And the rest of the psi r's are determined by this. That's actually something that's true for any marathi E theory, not just this one. Furthermore, the relations that need to be satisfied can be encapsulated in a single fact. This satisfies, this has the property. So the property I need to know, which gives me all the commutative diagrams I had up there, is a single commutative diagram. So I'm going to draw a part of the diagram for composing a deformation of f with another deformation of f. This is psi1. This is psi1 tensor the identity on A1. And then here, I'll put B tensor A2. And this came with some map I called mu star that classifies composing two isogenies. And the property I need is merely that there exists a ring homomorphism making that diagram commute. That's reasonable because it turns out that this map is always a monomorphism. So that's the relation, is just that fact. That this composite factors through a certain subring. And all the other commutative diagrams I wrote down for psi r and r prime, it's just this. And that's also true for any marathi E theory. So to actually use this, you want to know what EA2 is. So this I can insert in this particular example. I have 2 minutes. In this example, there's a pullback square describing E2. In fact, it's a universal pullback square. If I tensor it with any ring B, it's still a pullback square, which is what I need. It's true. So there's a pullback square of rings. Which is universal, which is that it remains a pullback after I tensor with B. But let me write it without it. So here's A2. Here's this map mu. It's an inclusion. Let me put my S's and T's in. Oh, I don't remember where they go. I think it's like this, the way I'm doing it. There's a pullback square like this. This map is just, in this case, it's just S. This is for a height 2 case only. This thing is called identity tensor W. Here, this is called pi. This is a pullback. I have to tell you what W is. So explicitly, it's given by some formula. There's A up there, so I have to tell you where little a and little d go. A goes to A prime, which is also named up there. D goes to D prime, which is D, where'd you go? A minus D squared. But let me tell you what this means. this expresses the map that represents a composite of isogenies. W is a map that expresses the dual of an isogeny. So in height 2, something special happens. If I have an isogeny of degree p, that always factors through, or sorry, that always factors the p series of G. So there always exists, and exists a canonical, or unique rather, map which I'll call f hat. So given an f, I can factor it uniquely through p. Sorry, I said that wrong, but I have this diagram. In general, that's true in general for an isogeny of degree p, but in this case, the degree of p is p squared, because we're height 2. So f also has degree p. And so W is the map from A1 to A1 that represents taking an isogeny to its dual. In the context of elliptic curves, this is related to something that's usually called the Frick involution. It's an operation on some kind of level structure associated with p isogenies. This diagram commutes. The fact that this diagram commutes is an encoding of this relation. That f hat composed with f is p. So you trace through backwards to see what it does. This side says take an f, I get an f and an f hat, I compose them. This side says take an f, forget about f, just remember the source, which is some deformation, and then do this. This map classifies an isogeny of degree p squared. It classifies p. That's what this diagram is. It's actually a pullback square. In the example, I could write down explicitly what it does. So this implicitly tells you what the subring A2 is. This is the most convenient way to say what it is. To write down this pullback square. So so I've actually described the whole structure, algebraic structure involved here. There's this operation. It makes this diagram. This exists, this factorization. So it satisfies this Frobenius isogeny. The one thing that's a little bit harder to say is that that Frobenius isogeny is actually witnessed by some non-additive operation. Usually, you hope you're in some object that's p torsion free, and then you don't have to worry about what that is, because it's determined just by knowing that there's a congruence. Okay, so this is an eminently computable thing. So I worked this out at the prime 2. It's really easy. In that case, it's harder as the prime increases. Yifei Zhu has computed these entirely for p and 3 and 5 for suitable supersingular curves. There's at least a plan for writing down something in general, which will probably need some input from elliptic curves. But sort of it's a formal process once you sort of get going. You just need a little bit about elliptic curves to make this go. So I'm overly out of time. So I'll just say this is a paradigm for what sort of should happen for power operations in elliptic cohomology. The moral is that this involves some kind of structure. In this case, it was deformations that you could push forward along homomorphisms. That was the input that I sort of the framework that I tried to state at the beginning. Deformations are something you push forward along homomorphisms. For elliptic curves, there are other structures you can attach, like level structures. And the idea is that when you can have some notion of pushing forward along homomorphisms, there should be power operations associated to that. So I'll start next time by saying that. And then I think I'll come back to this example and say more about this business about the fact that that you only need this one relation, which is the fact that in some sense, this coalgebra is quadratic. So I think that sort of has an interesting generalization that I'll talk about next time. OK, I'll stop there.